Before the first star was ever born, the universe spent hundreds of millions of years in complete darkness. No light, no heat, nothing but a vast, silent void. Welcome to the cosmic dark ages. How do you study an era you can never see? An age so dark, not a single photon of light existed. The answer lies not in the light that reached us, but in the light that never did. Every time we look deeper into space, we travel further back in time, past the first galaxies, past the first stars, into an age of absolute darkness. To understand what happened there, we need to start from the very beginning. But we joined this story very late. By the time we arrived, millions, billions of stars, planets, and galaxies had already been born, grown, and destroyed. Perhaps along with countless forms of life. By the time we got here, the universe had already been alive for over 13.5 billion years. But the universe had its own birth story. There was a time when nothing existed, not even a single particle of the matter we know. A period we call the cosmic dark ages. The biggest challenge, of course, is that the things we are trying to study and understand are at distances beyond comprehension. Take Voyager 2, which we launched just a few decades ago. Right now, it is more than 17 light hours away from us, and reaching even that distance is incredibly difficult with our current technology. Galaxies and celestial objects billions of light years away represent an enormous challenge for us. But there is a bright side to this. The light from an object that far away has been traveling for billions of years before it reaches us. So when we look at these objects, we are actually traveling through time. We can even see the very first galaxies and stars that ever formed. But what if we could look even further? Say we found the very first star somewhere at the edge of the observable universe. What would we find beyond it? The answer is nothing, just darkness. Because between the formation of the first atoms and the birth of the first star, there was no source of light anywhere in the entire universe. That is why we rarely come across much information or discussion about this period. After all, how do you talk about something you have never seen? But let's not underestimate ourselves. Humanity is far, far smarter than you might think. So what do we know about this era before the stars? Now, things are going to get a bit technical from here, but I promise I will bring it all together. This era, the cosmic dark ages, begins with a period known as recombination. Before this period, the universe was filled with hydrogen and helium atoms whose electrons had been stripped away. When atoms lose their electrons like this, we call them ionized. The reason for this was the incredibly high temperatures left over from the Big Bang. At extremely high temperatures, electrons cannot stay in their orbits around atoms. They break free, and the atoms become ionized. After 400,000 years of expansion, everything had finally cooled down enough for atomic nuclei to recapture their electrons. And the first atoms began to form. For the very first time, the universe became transparent. Things could finally be seen. And this is where we begin to see the very first light ever released. We know it as the cosmic microwave background, the oldest light we can see. But it would be a very long time before any new light appeared, because the cosmic dark ages had now begun. The reason was simple. There was no source to create new light. The universe was blanketed in atomic and molecular hydrogen and helium gas. The first stars born from this gas would become our true source of light. And those stars would burn through the gas and dust, igniting the era of reionization across the universe. At least, that is what we think happened. It is always the same tough question, right? How do we know? We will get there. But according to our best estimates, about 150 million years after recombination began, dense gas clouds started collapsing under their own gravity, and the first stars began to form. But these stars were enormous, absolutely massive, incomprehensibly large. Because back then, no other elements existed. The heavier elements on the periodic table had not yet been created. So with only hydrogen and helium as fuel, these stars could grow to staggering sizes. These stars would later become the factories that forged every other element in the universe. These incredibly large and hot stars were blasting the surrounding gas clouds with powerful infrared radiation, stripping electrons from atoms once again. Then they would quickly perish as colossal supernovae, scattering heavier elements across the cosmos and leaving behind the raw materials needed for the next generation of stars to be born. A pretty noble way to go, right? In this environment, the first primitive galaxies began forming, and they were producing stars at an incredible rate. But these galaxies began appearing inside bubbles of ionized plasma formed by the hydrogen they had burned through. So there were galaxies out there, but they were surrounded by an incredibly hot soup of plasma, an electron-free hydrogen broth, if you will, and they had wrapped themselves in these ever-growing bubbles. These primitive galaxies grew. Their ionized bubbles expanded and merged, and the process of fully reionizing the universe would take billions of years. And all of this was happening while the universe itself was expanding. At the start of the Dark Ages, the universe was about 1% of its current size. By the time reionization began, it had grown 100-fold. And since then, it has expanded another 10 times. So that is the story as we understand it. But the question still remains, how do we know all of this? First of all, we can actually see glowing galaxies from this era, including one that formed when the universe was just 400 million years old. But the real evidence is not the light that reached us. It is the light that never made it. Here is how it works. The hydrogen in the early universe was mostly transparent, but it could block very specific wavelengths of light. Every photon that carried the same energy as the electron transitions inside a hydrogen atom was captured. Two specific types of photons were in danger. In one case, their absorption tells us what the cosmic dark ages were like. In the other, it reveals how the age of reionization came to an end. To get a bit more technical, when an electron inside cold hydrogen gas flips its spin direction, it either emits or absorbs a radio photon with a wavelength of 21 centimeters. When the first stars were born, they heated the surrounding gas, and that gas began absorbing more 21-centimeter radiation than it was. This caused a dip in the spectrum of the cosmic microwave background radiation. The absorbed wavelength was then stretched by the expansion of the universe, shifting toward the red end of the spectrum. In other words, its wavelength grew longer. The amount of this shift tells us exactly when the first stars formed, because it was those very stars that triggered the absorption of these photons in the first place. They formed roughly 150 million years after the Big Bang, and they brought the cosmic dark ages to an end. Another type of photon tells us how the reionization era progressed. And to understand that, we need to talk about quasars. Remember those massive first stars? They were the ones that kicked off reionization, and along the way, they also forged the first heavy elements. When these types of stars exploded, they left behind black holes. These black holes were born inside gas-rich galaxies. They fed, and then they started merging with each other. They grew even larger, and the first supermassive black holes appeared. Colossal monsters, billions of times more massive than our sun. After consuming so much matter, these black holes, surrounded by superheated plasma, became the fuel for the first quasars. Quasars shining with the brightness of trillions of suns. Unfortunately, even our best telescopes were terrible at capturing these objects. But the James Webb Space Telescope might change that. Anyway, we can still see them as tiny red dots at incredible distances. The light from these quasars has traveled through the leftover hydrogen from the cosmic dark ages to reach us. And that gas has left its signature on the light. And here is our second type of photon, the Lyman alpha photon, with an exact wavelength of 121.57 nanometers. It is emitted or absorbed when the electron in hydrogen jumps between its ground state and second orbital, and hydrogen gas absolutely loves to devour this photon. So here is what happened. A Lyman alpha photon leaving a quasar during the reionization era would start its journey, and as the universe expanded, its wavelength stretched, which allowed it to escape the hydrogen gas. But photons with shorter wavelengths would stretch just enough to enter the danger zone and get caught. Photons at other wavelengths travel all that distance and reach us, but the universe is still expanding. Many photons get trapped along the way by remnants of the cosmic dark ages. And those energetic ultraviolet photons remain stuck there forever. When scientists plot all these photon wavelengths together, they can identify that photons within a certain range belong exclusively to quasars from the earliest ages of the universe. I told you that humanity is far smarter than you might think, and we should never sell ourselves short. So the light left over from the cosmic microwave background tells us how the dark ages ended, and the light from the first quasars shows us the final stages of reionization. Next up are our brand new telescopes. The James Webb Space Telescope and others like it will capture photons from this era at different wavelengths and create a complete map of this period. To take a photograph of the environment right after the Big Bang, I do not need to explain how monumental that would be. These will be discoveries that change everything we know. Findings that rewrite our understanding from scratch. Despite everything, I bow in respect before every scientist, named and unnamed, who dedicated their lives to researching, discovering, and sharing these monumental findings with all of us. And as always, until we meet again, I am glad you exist. With love.